Greetings, cosmic enthusiasts! Today, we're embarking on an extraordinary journey to explore one of the most captivating and enigmatic structures in our vast universe. The Whirlpool Galaxy, also known as M51. Prepare to be awestruck as we traverse through its shimmering spiral arms, witness regions of intense star formation, and observe a mesmerizing cosmic dance between two galaxies. Imagine, if you will, a colossal pinwheel of light, spinning gracefully in the dark expanse of space. This is M51, a grand design spiral galaxy that has captured the imagination of astronomers and stargazers for centuries. Located approximately 23 million light-years away in the constellation Canes Venatici, the Whirlpool Galaxy stands as a testament to the dynamic and ever-evolving nature of our cosmos. As we delve deeper into the mysteries of M51, we'll uncover the intricate processes that shape its stunning spiral structure. We'll explore how the gravitational tug-of-war between M51 and its smaller companion galaxy, NGC 5195, creates ripples of star formation that illuminate the galaxy's arms like cosmic beacons. But M51 is more than just a pretty face in the night sky. It's a cosmic laboratory where we can observe galaxy evolution in action. Through its study, astronomers have gained invaluable insights into the processes that shape galaxies throughout the universe, including our own Milky Way. From its discovery by Charles Messier in 1773 to the cutting-edge observations made by modern space telescopes, the Whirlpool Galaxy has continuously revealed new secrets. We'll journey through time to understand how our perception of M51 has evolved, and how it has revolutionized our understanding of the universe. So, fasten your seatbelts and prepare your minds for a cosmic adventure. We're about to spiral into the heart of one of the universe's most magnificent structures, where stars are born, galaxies collide, and the beauty of the cosmos is on full display. But here's the kicker. What we're about to discover about the Whirlpool Galaxy might just change everything you thought you knew about our universe. Stay tuned, because in the next few minutes, you'll learn about a mind-blowing feature of M51 that could rewrite our understanding of galaxy evolution. Trust me, you won't want to miss this cosmic revelation. If you're as excited as I am about unraveling the mysteries of the universe, don't keep this cosmic knowledge to yourself. Smash that like button to help this video reach more space enthusiasts like you. And if you want to stay on the cutting edge of astronomical discoveries, hit subscribe and click the bell icon to join our community at Exploring the Universe. Together, let's continue our journey through the cosmos, one galaxy at a time. Let's dive into the essential details of our celestial subject, the Whirlpool Galaxy. Think of this as M51's cosmic passport, providing us with key information about this magnificent structure. Our galaxy of interest goes by two primary names in astronomical catalogs. This designation comes from Charles Messier's famous catalogue of deep sky objects, where it's listed as the 51st entry. In the new general catalogue, a more comprehensive listing of deep sky objects, it's identified as number 5194. M51 is classified as a grand design spiral galaxy. But what does this mean? Spiral. It has a distinct disc-like structure with prominent spiral arms extending from a central core. Grand design. This term refers to the well-defined, symmetrical nature of its spiral arms. M51 is often used as the archetypal example of a grand design spiral galaxy. Compared to many other galaxies, M51 is substantial in size and luminosity, making it a favorite target for both professional and amateur astronomers. Like all celestial objects, M51 has its own neighborhood in the night sky. Constellation. Canes Venatici, the hunting dogs. This small northern constellation, often overlooked, is home to several interesting deep sky objects, with M51 being its crown jewel. Canes Venatici was created by Johannes Hevelius in the 17th century, split off from the larger constellation Ursa Major. Distance from Earth: approximately 23 million light-years. To put this in perspective, the light we see from M51 today left the galaxy when our early human ancestors were just beginning to use stone tools. This distance makes M51 one of the closest spiral galaxies to our Milky Way, yet still far enough to remind us of the vast scales of our universe. Size matters. Diameter: about 76,000 light-years. Compare this to our Milky Way, which is estimated to be about 100,000 light-years in diameter. If we could place M51 next to our galaxy, it would occupy about 3/4 of the Milky Way's diameter. A truly massive structure. No discussion of M51 is complete without mentioning its companion, NGC 5195, a dwarf galaxy engaged in a gravitational interaction with M51. This smaller galaxy is crucial to the Whirlpool's distinctive appearance and ongoing stellar processes. The interaction between these two galaxies is a cosmic dance that has been ongoing for millions of years, shaping the structure and evolution of both galaxies. The story of M51's discovery and our evolving understanding of its nature is a captivating journey through the history of astronomy. Let's explore this fascinating timeline. On October 13, 1773, the renowned French astronomer Charles Messier first observed M51. Messier was primarily searching for comets, but in the process, he catalogued numerous fuzzy objects that could be mistaken for comets. He described M51 as a very faint nebula, without stars, difficult to see in the telescope. At this time, the true nature of galaxies was unknown, and such objects were generally termed nebulae. Messier added this object to his famous catalogue as the 51st entry, hence the designation M51. On April 5, 1845, a groundbreaking observation was made by William Parsons, the 3rd Earl of Rosse, also known as Lord Rosse. Using his massive 72-inch reflector telescope, nicknamed the Leviathan of Parsonstown, Lord Rosse observed M51 in unprecedented detail. He was the first to discern and document the spiral structure of M51. Lord Rosse made a detailed drawing of M51, clearly showing its spiral arms, which caused a sensation in the astronomical community. This observation marked M51 as one of the first recognized spiral nebulae, though its true galactic nature was still not understood. The discovery of spiral structure in celestial objects was revolutionary, opening up new questions about the nature of these nebulae. As telescope technology improved, more details of M51 and other spiral nebulae were revealed. A great debate arose in the astronomical community. Were these spiral nebulae part of our Milky Way, or were they island universes, distant galaxies in their own right? Astronomers like Heber Curtis argued that spiral nebulae were separate galaxies, while others like Harlow Shapley contended they were part of the Milky Way. The debate was finally settled in the 1920s, thanks largely to the work of Edwin Hubble. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble was able to resolve individual stars in some nearby galaxies. In 1923, Hubble identified Cepheid variable stars in the Andromeda Galaxy, allowing him to calculate its distance. This proved that Andromeda, and by extension other spiral nebulae including M51, were indeed separate galaxies far outside our Milky Way. With its status as an external galaxy confirmed, M51 became a key object of study for understanding galactic structure and evolution. Advanced telescopes, including space-based observatories like Hubble, have provided increasingly detailed views of M51. These observations have revealed intricate details of its spiral arms, star-forming regions, and its interaction with its companion galaxy. The Whirlpool Galaxy, M51, is a visual masterpiece that has captivated astronomers and space enthusiasts alike. Its structure is a testament to the complex and beautiful nature of spiral galaxies. Let's delve into the key components that make M51 such a spectacular sight. M51 is classified as a grand design spiral galaxy due to its prominent, well-organized spiral structure. The galaxy features two main spiral arms that wrap around the galactic center, creating a near-perfect pinwheel shape. These arms are not just visual features, but are density waves, areas of higher stellar and gas concentration that rotate around the galaxy. The symmetry of these arms is particularly striking, making M51 an exemplar of spiral galaxy structure. Within the main spiral arms, smaller structures called spurs and feathers can be observed, adding intricate detail to the overall design. At the heart of M51 lies a compact, intensely bright nucleus. This central region is home to the oldest stars in the galaxy and likely harbors a supermassive black hole. The core's brightness is due to its high density of stars and the presence of hot gas. Surrounding the core is a bulge, a spheroidal component that extends above and below the galactic disk. The interplay between the bright core and the spiral arms creates a stunning contrast that defines M51's appearance. The spiral arms of M51 are dotted with numerous bright blue regions. These are areas of active star formation, where new stars are being born from collapsing clouds of gas and dust. These regions, also known as HII regions due to their ionized hydrogen, appear blue because they contain hot, young, massive stars. The presence of these star-forming regions in the arms supports the density wave theory of spiral arm formation. These areas are crucial for understanding the ongoing evolution and renewal of the galaxy. Interwoven with the bright spiral arms are dark lanes and patches. These dark areas are vast clouds of interstellar dust that absorb and block light from stars behind them. The dust lanes add depth and texture to the galaxy's appearance, enhancing its three-dimensional quality. These dust regions are important nurseries for future star formation. The interplay between bright star-forming regions and dark dust lanes creates a striking visual contrast within the spiral arms. One of the most intriguing features of M51 is the visible connection to its smaller companion galaxy, NGC 5195. Streams or bridges of gas, dust, and stars can be seen stretching between M51 and NGC 5195. These bridges are the result of gravitational interactions between the two galaxies. They demonstrate the dynamic nature of galactic interactions and provide insight into the processes of galactic mergers. The presence of these bridges contributes to the ongoing star formation in M51 by compressing gas and triggering stellar birth. Additional structural elements. While not as prominent as in some galaxies, M51 has a weak bar structure in its central region. Beyond the main spiral structure, a faint outer ring can be detected, likely formed by the gravitational influence of NGC 5195. Although not visible to the naked eye, M51 has a complex magnetic field structure that influences gas dynamics and star formation. The structure of M51 is not just a static feature but a dynamic system in constant evolution. The interaction with NGC 5195 continues to shape the galaxy, influencing its spiral arms, triggering star formation, and gradually altering its overall structure. This makes M51 not only a beautiful object to observe but also a valuable cosmic laboratory for studying galactic dynamics and evolution. NGC 5195, the smaller companion galaxy to M51, plays a crucial role in shaping the appearance and evolution of the Whirlpool Galaxy. Let's explore this cosmic dance partner in detail. NGC 5195 is generally classified as a dwarf galaxy, significantly smaller and less massive than M51. Its exact classification has been a subject of debate among astronomers. Some classify it as a lenticular galaxy, which is an intermediate type between elliptical and spiral galaxies. Lenticular galaxies have a central bulge and a disk but lack distinct spiral arms. Others argue that due to its interaction with M51, NGC 5195 has become too distorted to fit neatly into standard galaxy classifications, thus labeling it as an irregular galaxy. The uncertainty in classification highlights the dynamic nature of galactic interactions and the challenges in categorizing galaxies undergoing active transformations. NGC 5195 is approximately one-third the size of M51, making it a substantial dwarf galaxy. Estimated diameter, roughly 25,000 light-years, compared to M51's 76,000 light-years. Despite its smaller size, NGC 5195 contains billions of stars and significant amounts of gas and dust. The size difference between the two galaxies is key to understanding the dynamics of their interaction. The interaction between NGC 5195 and M51 is the defining feature of this galactic pair. NGC 5195's gravity pulls on M51, causing distortions in the larger galaxy's spiral structure. As NGC 5195 orbits M51, it creates tidal forces that compress gas in M51, triggering star formation. The interaction has led to the exchange of gas and dust between the two galaxies, visible as streams or bridges of material. Astronomers believe NGC 5195 has made at least one close pass through or near M51's disk. This close encounter likely occurred about 500 to 600 million years ago. The current visible effects are the aftermath of this passage, as well as ongoing gravitational interactions. The gravitational pull of NGC 5195 has helped to amplify and maintain M51's prominent spiral structure. The interaction has caused some asymmetry in M51's spiral arms, with one arm appearing slightly more disturbed than the other. Compression of gas due to NGC 5195's gravity has triggered bursts of star formation in M51, particularly visible in the spiral arms closest to NGC 5195. The interaction has significantly affected NGC 5195's own structure and evolution. Some of NGC 5195's outer layers of gas and stars have been stripped away by M51's gravitational pull. The galaxy's shape has been distorted from its original form, contributing to its uncertain classification. While the interaction has sparked star formation in M51, NGC 5195 itself shows signs of reduced star formation, possibly due to gas depletion. The long-term fate of NGC 5195 and M51 is a subject of ongoing research. Many astronomers predict that NGC 5195 will eventually be fully absorbed by M51, a process that could take billions of years. Alternatively, NGC 5195 might continue to orbit M51 for an extended period, gradually losing more of its material to the larger galaxy. The M51 NGC 5195 system serves as a valuable nearby example of galaxy interaction and minor mergers. Studying this pair helps astronomers understand how galaxies grow through mergers and acquisitions, the impact of gravitational interactions on galactic structure and star formation, the process of satellite galaxy absorption by larger galaxies, the cosmic dance between M51, the Whirlpool Galaxy, and NGC 5195 is what makes this system truly special. This interaction is a prime example of galactic dynamics and evolution in action, offering astronomers a unique opportunity to study these processes in real time. The interaction is believed to have begun approximately 100 million years ago. This time frame is relatively recent in cosmic terms, making it an ongoing and dynamic process. The effects we observe today are the result of this prolonged interaction, showcasing how galaxies evolve over millions of years. NGC 5195 has passed through or near M51's disk at least twice. The first passage likely occurred about 500 to 600 million years ago. A second, more recent passage happened roughly 50 to 100 million years ago. These multiple encounters have had cumulative effects on both galaxies, intensifying the structural changes and star formation processes. As NGC 5195 moves close to M51, its gravitational pull creates significant disturbances in M51 structure. These gravitational forces create tidal tails and bridges of material between the two galaxies. The interaction also causes asymmetries in M51 spiral arms, with one arm appearing more disturbed than the other. The passages of NGC 5195 through or near M51 have caused shock waves to propagate through both galaxies. These shock waves compress the gas and dust in M51, particularly in its spiral arms. The compression of gas clouds is a crucial trigger for star formation, as it causes these clouds to collapse under their own gravity. The most dramatic result of this interaction is the intensification of star formation in M51 spiral arms. Regions of active star formation, known as HII regions, are clearly visible as bright blue areas along the spiral arms. This enhanced star formation is particularly noticeable in the areas closest to NGC 5195, where the gravitational effects are strongest. The rate of star formation in M51 is estimated to be 2 to 3 times higher than it would be without the interaction. The interaction has led to the exchange of gas and dust between the two galaxies. Streams of material can be observed flowing from NGC 5195 towards M51. This exchange of material fuels further star formation and contributes to the overall evolution of both galaxies. The interaction has amplified M51's spiral structure, making it more pronounced and well-defined. The outer regions of M51 show signs of disturbance, with some stars and gas being pulled towards NGC 5195. NGC 5195 itself has been significantly distorted by the interaction, losing its original shape and classification. The ongoing interaction is gradually bringing NGC 5195 closer to M51. Over billions of years, this process is likely to result in a full merger of the two galaxies. This merger will eventually transform M51 from a spiral galaxy into an elliptical galaxy, a process that astronomers believe is common in galactic evolution. The M51 NGC 5195 system serves as a crucial laboratory for studying galactic interactions. It provides insights into how galaxies grow and evolve through mergers and acquisitions. The system helps astronomers understand the role of interactions in triggering star formation and shaping galactic structures. Studying this interaction helps us understand similar processes that may have occurred in our own Milky Way's history. It provides clues about the formation of larger galaxies through the absorption of smaller satellite galaxies. The M51 system offers a glimpse into the dynamic and ever-changing nature of the universe on a galactic scale. The interaction between M51, the Whirlpool Galaxy, and NGC 5195 has profound and far-reaching consequences, dramatically altering both galaxies. This cosmic dance showcases the dynamic nature of galactic evolution and provides astronomers with a living laboratory to study these processes in real time. The gravitational forces between the two galaxies compress vast clouds of gas and dust. This compression increases the density of these clouds, causing them to collapse under their own gravity. As a result, new stars are born at an accelerated rate, particularly in the spiral arms of M51. Intense pockets of star formation, known as starburst regions, are visible throughout M51's spiral arms. These regions appear as bright blue areas, indicating the presence of hot, young, massive stars. Clusters of young, bright stars are prominently visible in the spiral arms. These clusters, some containing thousands of stars, form as a direct result of the gravitational interaction. They are often surrounded by glowing nebulae, further evidence of recent star formation. The increased star formation leads to a higher rate of supernovae in M51. These explosive stellar deaths further enrich the interstellar medium with heavy elements, fueling future generations of stars. The gravitational pull of NGC 5195 amplifies M51's spiral structure. The arms become more pronounced and well-defined, creating the iconic whirlpool appearance. This enhancement is particularly noticeable on the side of M51 closest to NGC 5195. Bridges of matter form between M51 and NGC 5195, consisting of gas, dust, and stars. These bridges are visible evidence of the gravitational connection between the two galaxies. Tidal tails extend from M51, stretching into intergalactic space, showcasing the powerful gravitational forces at play. The interaction creates asymmetries in M51 structure. One spiral arm often appears more disturbed and elongated than the other. This asymmetry provides clues about the orbital path of NGC 5195 and the history of their interaction. The gravitational forces cause a subtle warping of M51's galactic disk. This warping is most noticeable in the outer regions of the galaxy. Gas and dust are pulled from one galaxy to another by their mutual gravitational attraction. This transfer is most pronounced from NGC 5195 towards M51 due to the larger galaxy's stronger gravitational field. Streams of material can be observed flowing between the two galaxies. These streams create a cosmic bridge, visually connecting the two galaxies. The exchange of material leads to a mixing of gas and dust from both galaxies. This mixing can potentially lead to changes in the chemical composition of both galaxies over time. The transferred material provides fresh fuel for star formation, particularly in M51. This process contributes to the ongoing cycle of stellar birth and death in the interacting system. The gravitational interaction creates density waves that propagate through M51's disk. These waves are similar to ripples in a pond, but on a cosmic scale. The density waves play a crucial role in shaping and maintaining M51's spiral structure. As the waves move through the galaxy, they compress gas and trigger star formation, reinforcing the spiral pattern. The density waves create dynamic structures within the galaxy, such as spurs and feathers in the spiral arms. These features are constantly evolving, showcasing the dynamic nature of galactic structures. The continuous propagation of these waves contributes to the long-term evolution of M51's structure. Over millions of years, these waves help to redistribute matter within the galaxy, influencing its overall shape and composition. Studying these density waves in M51 provides insights into similar processes that may occur in other spiral galaxies, including our own Milky Way. The Whirlpool Galaxy, M51, serves as a cosmic laboratory for astronomers, offering invaluable opportunities to study various astronomical phenomena. Its proximity and the ongoing interaction with NGC 5195 make it an ideal subject for numerous scientific investigations. Here's a detailed look at the key areas of scientific observation. High-resolution imaging allows astronomers to study M51's spiral structure in detail. Observations of the galaxy's core, bulge, disk, and spiral arms provide insights into how these components form and evolve. M51 offers a clear view of star-forming regions, allowing scientists to study the conditions necessary for stellar birth. Observations in multiple wavelengths, optical, infrared, radio, reveal different aspects of the star formation process. The well-defined spiral arms of M51 serve as a model for understanding spiral density wave theory. Scientists use M51 to study how spiral structures are maintained over long periods. Spectroscopic studies of M51 reveal its chemical composition, providing clues about its age and history. Researchers analyze how elements are distributed throughout the galaxy, offering insights into galactic chemical evolution. The ongoing interaction between M51 and NGC 5195 allows real-time study of gravitational forces between galaxies. Tidal distortions and bridges of material between the galaxies are closely analyzed. Scientists observe how galaxy interactions trigger and enhance star formation. Comparison of star formation rates in different regions of M51 helps quantify the impact of the interaction. Studies focus on how gas is transferred and compressed during galactic interactions. Observations of gas flows provide data for computer simulations of galaxy mergers. M51 serves as a model for understanding how galaxies grow and change through mergers and acquisitions. Researchers use observations of M51 to refine models of galaxy evolution over cosmic timescales. Several supernovae have been detected in M51 over the past few decades, allowing studies of their frequency and spatial distribution.
Notable supernovae include SN 1994I, SN 2005CS, and SN 2011DH.
The different types of supernovae observed in M51, e.g., Type Ia, Type II, provide data on stellar evolution and galactic chemical enrichment. Observations of supernova remnants in M51 offer insights into the aftermath of these explosive events and their impact on the surrounding interstellar medium. Type Ia supernovae in M51 have been used to refine distance measurements to the galaxy, contributing to the cosmic distance ladder. Observations of M51's rotation provide evidence for the presence of dark matter. Scientists analyze how the galaxy's rotation speed varies with distance from the center to infer the distribution of dark matter. While not as prominent as in clusters of galaxies, weak gravitational lensing effects in M51 can provide clues about its dark matter halo. Researchers create complex models of M51's mass distribution, including both visible and dark matter components. These models are continually refined based on new observational data. The dark matter distribution in M51 is compared with that of other galaxies to understand common features and variations. Radio telescopes reveal the distribution of neutral hydrogen and other gases in M51. These observations help map the galaxy's overall structure and gas dynamics. Infrared telescopes like Spitzer have mapped the distribution of dust and cool gas in M51. These observations are crucial for understanding star formation processes. X-ray telescopes like Chandra have detected numerous X-ray sources in M51, including black holes and neutron stars. These observations provide insights into high-energy phenomena in the galaxy. UV telescopes like Galex have revealed the distribution of young, hot stars in M51. This data is essential for understanding recent star formation history. Advanced ground-based telescopes using adaptive optics have provided incredibly detailed images of M51 structure. Radio interferometers like ALMA have allowed for high-resolution studies of gas and dust in M51. Hubble Space Telescope observations have provided unparalleled views of M51 structure and star-forming regions. Future observatories like the James Webb Space Telescope promise even more detailed observations. The Whirlpool Galaxy, M51, is a treasure trove of astronomical phenomena, and observing it across the electromagnetic spectrum reveals a wealth of information about its structure, composition, and ongoing processes. Each wavelength of light tells a unique story about M51, offering astronomers a comprehensive view of this magnificent galaxy. Let's explore how M51 appears in different wavelengths and what each reveals. In visible light, M51 showcases its iconic spiral structure with striking clarity. The galaxy appears as a swirling pinwheel of blue-white spiral arms surrounding a yellowish core. Bright blue regions in the spiral arms indicate areas of recent star formation, where hot, young stars dominate. The yellower central bulge suggests the presence of older, cooler stars. Dark dust lanes are visible, tracing the galaxy's spiral structure. Visible light observations provide crucial information about the galaxy's overall structure and star formation patterns. They allow astronomers to study the distribution of different stellar populations within the galaxy. In infrared, M51 takes on a different character, with the spiral arms appearing as reddish filaments. The overall structure is smoother compared to visible light images. Infrared light penetrates dust clouds, revealing stars and structures hidden in visible light. It highlights the distribution of cooler dust and gas throughout the galaxy. Older, cooler stars become more prominent in infrared. Infrared observations are crucial for understanding the galaxy's dust content and distribution. They provide insights into the galaxy's star formation history and the presence of older stellar populations. Infrared data helps in estimating the total mass of stars in the galaxy. In X-ray light, M51 appears as a collection of bright points and diffuse glows rather than a cohesive spiral structure. X-ray observations highlight high-energy phenomena within the galaxy. Bright points often indicate the presence of X-ray binaries, systems where a normal star orbits a neutron star or black hole. Diffuse X-ray emission can reveal hot gas in the galaxy, often associated with recent supernova explosions. X-ray data provides information about the most energetic processes in the galaxy. It allows astronomers to study the population of compact objects like neutron stars and black holes. X-ray observations can reveal evidence of past supernova explosions and their impact on the galactic environment. In radio wavelengths, M51 appears as a less defined structure with bright regions corresponding to areas of intense activity. Radio observations map the distribution of cold hydrogen gas throughout the galaxy. They highlight regions of active star formation, often appearing as bright spots in the spiral arms. Radio waves can also reveal the presence of synchrotron radiation, indicating magnetic fields and relativistic electrons. Radio data is crucial for understanding the galaxy's gas content and distribution. It provides insights into the process of star formation and the life cycle of gas in the galaxy. Radio observations can reveal the presence and structure of magnetic fields within the galaxy. In UV light, M51 spiral arms appear as bright, blue-white structures. The galaxy's core is less prominent compared to visible light images. UV light primarily comes from young, hot stars, making it an excellent tracer of recent star formation. It highlights the most active star-forming regions in the galaxy. UV observations are key to understanding the current star formation rate in the galaxy. They help astronomers trace the distribution of the youngest stellar populations. Gamma-ray observations of M51 are less detailed due to the limitations of gamma-ray telescopes. The galaxy appears as a faint source of high-energy gamma radiation. Gamma rays indicate the presence of extremely energetic processes, such as cosmic ray interactions or potential gamma-ray bursts. While less prominent for M51, gamma-ray observations can provide insights into the most extreme high-energy phenomena in galaxies. Astronomers often combine observations from multiple wavelengths to create composite images of M51. These images provide a more complete picture of the galaxy's structure and processes. Multi-wavelength studies allow astronomers to correlate different phenomena and understand their relationships. They provide a comprehensive view of the galaxy's ecology, from cool gas to hot, newly formed stars. The Whirlpool Galaxy, M51, and its companion NGC 5195 are engaged in a cosmic dance that will shape their future over billions of years. Astronomers can use computer simulations and our understanding of galactic dynamics to project the likely fate of this interacting system. Let's explore the potential future of M51 in detail. The gravitational interaction between M51 and NGC 5195 will continue for hundreds of millions of years. This prolonged interaction will lead to further distortions in M51's spiral structure. The continued gravitational forces will trigger more episodes of intense star formation in both galaxies. This may lead to periodic starbursts, where large numbers of stars form in relatively short cosmic timescales. Gas and dust will continue to be exchanged between the two galaxies. This exchange may lead to the formation of new stellar populations with mixed chemical compositions. Over time, NGC 5195's orbit around M51 will decay due to gravitational forces and dynamical friction. This orbital decay will bring the two galaxies closer together, intensifying their interaction. The complete merger of M51 and NGC 5195 is expected to occur in approximately 1 to 2 billion years. This time frame is based on computer simulations and our understanding of similar galactic interactions. The galaxies will make several close passes, with each pass causing more significant distortions. Eventually, the cores of the two galaxies will merge, forming a single, chaotic system. Over time, the merged system will settle into a new, stable configuration. During the merger, the beautiful spiral structure of M51 will be severely disrupted. Tidal tails and bridges will become more pronounced, potentially extending far into intergalactic space. The merger will trigger an enormous burst of star formation as vast clouds of gas collide and compress. This starburst phase may briefly make the merging system much brighter than the individual galaxies were previously. The supermassive black holes at the centers of both galaxies will eventually merge. This merger could produce gravitational waves detectable by future space-based gravitational wave observatories. The violent process of merging will destroy the delicate spiral structure of M51. Gas and dust will be either consumed in star formation or ejected from the system. As the merged system relaxes, it will likely take on an elliptical shape. The exact shape, from nearly spherical to highly elongated, will depend on the details of the merger process. The new elliptical galaxy will contain a mix of old stars from both original galaxies and new stars formed during the merger. Over time, as star formation ceases, the galaxy will become dominated by older, redder stars. Most of the cold gas in the system will be used up in the starburst phase or heated to high temperatures. This depletion of cold gas will lead to a significant reduction in star formation after the merger. The resulting elliptical galaxy will be larger and potentially more luminous than either of the original galaxies. It may become a dominant galaxy in its local galactic neighborhood. The merger will create an extended halo of stars and globular clusters around the new elliptical galaxy. This halo will continue to evolve slowly over billions of years. The merged M51, NGC 5195 system may capture smaller satellite galaxies over time. These minor mergers could contribute to the growth of the galaxy over cosmic timescales. The new galaxy will continue to interact with the intergalactic medium, potentially accreting small amounts of gas. This interaction may lead to low levels of star formation long after the main merger event. Studying the future of M51 provides insights into the process of galaxy mergers throughout the universe. It helps astronomers understand how galaxies grow and evolve over cosmic time. The M51 NGC 5195 system serves as a model for how many elliptical galaxies may have formed through mergers of spiral galaxies. Projections of M51's future help scientists understand the complex relationship between galaxy mergers and star formation rates. The Whirlpool Galaxy, M51, serves as a crucial cosmic laboratory, offering astronomers invaluable insights into various aspects of galactic and stellar processes. Its significance extends far beyond its stunning visual appeal, contributing substantially to our understanding of the universe. Let's explore in detail how M51 enhances our knowledge in several key areas. M51 provides a snapshot of galaxy evolution in action, allowing astronomers to study how galaxies change over time. By comparing M51 to galaxies at different stages of evolution, scientists can piece together a more complete picture of galactic life cycles. The interaction between M51 and NGC 5195 demonstrates how a galaxy's environment can dramatically affect its evolution. This helps in understanding how galaxies in different cosmic environments, e.g., clusters versus isolated regions, evolve differently. M51 offers insights into how spiral galaxies can transform into other types, e.g., elliptical, through interactions and mergers. This supports theories about the origin of different galaxy morphologies observed in the universe. By studying the distribution of elements in M51, astronomers can trace how galaxies become enriched with heavier elements over time. This contributes to our understanding of the chemical evolution of the universe as a whole. M51 and NGC 5195 showcase an ongoing interaction, allowing scientists to study various stages of galactic encounters in real time. This helps in refining models of galaxy collisions and mergers across cosmic timescales. The clear tidal structures in M51 provide excellent examples of gravitational effects in galactic interactions. These observations help validate and improve computer simulations of galaxy mergers. The interaction between M51 and NGC 5195 reveals how gas flows and redistributes during galactic encounters. This informs our understanding of how matter is transferred between galaxies and within galactic systems. Studying systems like M51 helps astronomers estimate the frequency of galaxy mergers in the universe. This contributes to our understanding of how galaxies grow and evolve through mergers and acquisitions. M51 provides a clear example of how galactic interactions can trigger enhanced star formation. Scientists can study the specific conditions and processes that lead to increased star formation rates during galaxy interactions. By comparing star formation rates in different regions of M51, astronomers can measure how efficiently gas is converted into stars under various conditions. This helps in understanding the factors that control star formation on galactic scales. M51 offers insights into the conditions that lead to starburst events, where star formation rates dramatically increase. This contributes to our understanding of starburst galaxies observed throughout the universe. The galaxy allows for the study of how newly formed stars and supernovae affect their surrounding environment. This feedback process is crucial for understanding the self-regulation of star formation in galaxies. M51's well-defined spiral structure provides an excellent laboratory for testing theories of spiral arm formation and dynamics. It helps in understanding how spiral patterns are maintained over long periods despite differential rotation. The galaxy serves as a prime example for studying density wave theory, which explains the persistence of spiral arms. Observations of M51 help refine models of how stars and gas interact with spiral density waves. Studies of M51's rotation curve contribute to our understanding of galaxy dynamics and mass distribution. This includes insights into the distribution of dark matter in spiral galaxies. M51 allows for detailed studies of the interstellar medium in spiral galaxies, including the distribution of gas and dust. This enhances our understanding of the complex ecosystem within spiral galaxies. The detection of multiple supernovae in M51 helps astronomers estimate supernova rates in spiral galaxies. This contributes to our understanding of stellar evolution and galactic chemical enrichment. M51 provides opportunities to study different types of supernovae in a known galactic context. This aids in refining models of stellar evolution and the end stages of different types of stars. Studies of M51's core contribute to our understanding of supermassive black holes in galactic centers. This includes insights into how black holes interact with their galactic environments. M51 has been used to search for evidence of intermediate mass black holes, helping to fill the gap in our understanding between stellar mass and supermassive black holes. As a relatively nearby galaxy, M51 serves as an important rung in the cosmic distance ladder. Accurate distance measurements to M51 help calibrate methods used to measure distances to more distant galaxies. M51 is frequently used to test and calibrate various observational techniques across the electromagnetic spectrum. This helps in developing and refining methods used to study more distant and fainter galaxies. The Whirlpool Galaxy, M51, stands as a testament to the dynamic and ever-evolving nature of our universe. Far more than just a beautiful celestial image, it serves as a living laboratory for astronomers and a source of wonder for all who gaze upon it. As we conclude our journey through the wonders of the Whirlpool Galaxy, I'd like to invite you, our viewers, to engage further with this fascinating topic in our channel. Read through other viewers' comments and engage in discussions. Astronomy is even more exciting when shared with fellow enthusiasts. If you have questions about M51 or any related topics, don't hesitate to ask. Our community is here to learn and grow together. If you enjoyed this video and found it informative, please give it a thumbs up. Your likes help our content reach more space enthusiasts. Haven't subscribed yet? Hit that subscribe button to join our community of cosmic explorers. Don't forget to click the notification bell to stay updated on our latest galactic adventures. If you know someone who would enjoy learning about M51, share this video with them. Let's spread the awe and wonder of the cosmos. Consider sharing your favorite fact from this video on your social media. You might inspire someone to look up at the night sky with new appreciation.